Okay, in here, let's think about how an electric motor works. So, what is an electric motor? Electric motor is a device to generate rotational motion using electric current. And this is an example. And of course, in this display example, its casing is cut out, right? So it's cut out so that you can see inside. And you can see there is a lot of electric wire wound many times. So it looks very complicated. But here we will think about the simplest example. Okay. And basically the way electric motor works is based on the magnetic force acting on current carrying wires. Okay. And let's consider, as a simplest example, let's consider a current loop in a magnetic field. So, okay, in this simplified example, we have a rectangular loop in which the current is going to the left at the bottom, so it looks like it's going clockwise if you see it from this side, and it's placed inside the magnetic field. So given the direction of the magnetic field, this must be the north pole and this must be the south pole, right? And now let's assume that this loop has a rotational axis along here. So it's fixed here, so it cannot move, but it can only rotate around this axis. Okay, so that's for simplicity. And then, of course, if there is a magnetic field and a current, there must be magnetic force, right? It's already drawn here. There's one force acting on this side and the other force acting on that side, and they are along opposite directions. Why? Because the direction of the current here is going up, but its current is going down on the other side. So therefore, the direction of the current are opposite. So therefore, the directions of their forces are also opposite, right? And then it's the simplified figure is drawn here in a two-dimensional figure. Okay. One thing I forgot to mention: the size of this loop. This loop has a length A on top and bottom, and on two sides is length of this edge is B. Okay, so therefore you are looking it down. So looking down, this is a length A, and on this part, this length is going into this screen. Okay, so this length of that edge going into the screen will be B, and then you can see the current is going coming out here. And then the current is going in here, and then there are two opposite magnetic forces. Okay, and at this moment, this loop, the vector, normal vector, which is perpendicular to the plane of loop, is actually at an angle theta with respect to the direction of the magnetic field. Okay, and then again, make sure that all the magnetic force must be perpendicular to the direction of the current and also direction of the magnetic field, right? Okay, and then let's try to calculate the torque. Why torque? Actually, in this case, these two forces actually cancel each other, so there is no net force, but they are acting on different locations. So as a result, this can rotate like this, right? So it effectively creates a torque. And what is torque? If you remember, try to remember, torque was defined as an R vector cross F vector. And what is R vector here? So R vector is the vector representing the distance between the rotational axis and the location where this force is acting, right? So if this is a force vector, and then this is the R vector, then it will rotate like this. And then in this case, this torque vector will be coming out of the screen, right? Okay. Okay. Please make sure you understand this from the spring semester, and let's try to calculate the torque in this current loop. So there are two forces, so we have to calculate two torques separately and then add them together. Okay, in this case, what is the distance between the rotational axis and then the location where the force is acting? of course, it is half of A, right? So here the half of A corresponds to the size of this R vector, okay? And then how about the size of the force vector? The size of the force vector must be B multiplied by large B. The small b is corresponds to the L, which is the length of the loop of the wire in this case, and then a large B is of course magnetic field. And then there must be another term which is sine theta. Why do we need sine theta? Because torque is the R cross product of F. So therefore we need the angle between these two vectors. So here, given this example, what is the angle between this R vector and then the force vector? Okay, this angle is actually the same angle as this, so which is theta. So that's why you have sine theta. Okay, and how about the other side? On this side, we already said that the size of this force is the same, and then also the size of this distance is the same, and angle is the same, right? Okay, so they are adding up, and eventually you have this. Okay, I multiplied by AB multiplied by the magnetic field and also sine theta of the angle. Okay, and well, here we thought about only one loop, but as you can see in this example, you will typically use many loops in order to create large torque, right? So therefore, if you have n loops, which means that if you made n turns, then of course each loop will contribute the same amount of torque. So therefore, finally, you simply have to multiply by n. So what you get is n IAB multiplied by b sine theta. Okay, and in fact, what is small a multiplied by small b? This is in fact an area of this loop, right? This loop area is simply the small a multiplied by small b. So let's use large A to represent the area. And then once you have this, this magnetic field is a vector. And then we learned previously we can represent the area as a vector. So finally, you can say the torque, which is a vector, is a cross product between this area vector and magnetic field vector multiplied by the size of the current and then the number of loops. Okay, and then the figure will look like this. Okay, this is the torque generated when the electric current goes around the loop in a magnetic field. Okay, and in fact, just one note. In fact, in order to generate continuous rotation in real electric motors, the direction of current must be reversed repeatedly, which means it has to go plus and minus continuously. And we will study this a little bit detailed in the classroom. I will explain this in the classroom. Okay. Okay, and finally we will discuss the magnetic dipole moment. Okay, try to remember that in early part of this lecture, we learned that the magnetic field of a current loop is similar to the magnetic field of a permanent magnet. Okay, so they were related. So based on this idea, we will define a magnetic dipole moment of a coil as the multiplication between the number of turns and the current and then the area of each turn. So it can be mathematically written this way, and we will use a symbol mu vector to represent the magnetic dipole moment. So if we define it this way, then the torque on the dipole, torque on the magnetic dipole due to the external field can be now written this way. This is exactly the same equation we had in the previous slide, and now this part actually can become the magnetic dipole. So therefore, finally, the torque is simply the cross product between the magnetic dipole and the magnetic field. So basically, this magnetic dipole represents how strong or how large the this magnetic moment is. So, and this is actually, if you remember the electric dipole moment from the chapter 22, this form of the torque is in fact very similar to the torque of the electric dipole moment, which is P vector, inside the electric field, which is E vector, right? And there, the electric dipole moment was defined as the charge multiplied by the displacement vector between these two poles, right? Which was a D vector. So therefore, now when you compare the electric dipole moment and the magnetic dipole moment, so instead of Q in the electric dipole moment, you have I current in the magnetic dipole moment, and instead of this displacement vector in the electric dipole moment, you have an area vector in the magnetic dipole moment. Okay, and then for electric dipole moment, you have just one plus charge and one minus charge. But in the case of magnetic dipole moment, you can make many loops. So that is why we have N here. But basically, N multiplied by I represent the total current making one turn. Okay, so this expression of this magnetic dipole moment is very similar and in fact equivalent to defining this electric dipole moment, so that electric dipole moment will experience torque inside the electric field, and magnetic dipole moment will experience torque in magnetic field. So they look very similar, right? And so given the similar form of this torque between magnetic dipole moment and electric dipole moment, now we can deduce the idea that the potential energy of the magnetic dipole moment inside the magnetic field is again similar to the potential energy of the electric dipole moment in an electric field. So therefore, remember this was the expression of the electric dipole moment potential energy in the electric field. So therefore, using this similarity, now we will express the potential energy of the magnetic dipole moment in the magnetic field as a dot product between magnetic dipole moment and then the magnetic field. And then again, why do we have the minus sign? It is because when the magnetic moment is oriented exactly parallel to the magnetic field, then that will be the lowest point of energy. So the minimization of potential energy. So therefore, for that reason, we just put minus here. Okay. So remember, between the magnetic dipole moment and the magnetic field, the torque was a cross product between them, and potential energy is a dot product between them multiplied by the minus sign, and everything here is very similar and in fact look the same between electric dipole moment and electric field, right? Okay, so that's it for this chapter. Okay, so finally let's make a summary. From this lecture, you have learned the definition of magnetic field and the magnetic force by a magnetic field on a moving charge. And we also learned the magnetic force by a magnetic field on a wire carrying current. And also the basic mechanism of electric motor. And finally, we learned the magnetic dipole moment and its analogies to electric dipole moment. Okay, so please try to review it. And in the next online lecture, we will study the magnetism to the next step. So we will study these many things. Okay, but anyway, so I will see you on Thursday, and probably there will be many things I will explain. And if you have any questions, please bring your questions to the classroom lecture. Okay, I'll see you then.